Let's jam. 3.1, we're in the middle of it here. We looked at exponential functions. What do you guys say? Cool, pretty cool functions, or like sort of? They're functions. But one of the last few functions you guys do as far as algebra class is concerned, here it is. And then we go on to trig.
For exponentials, you always have to make a table.
No, eventually we know what they look like, especially at critical point 0, 1. And then we'll know the next one, which is called 1, comma a. Based upon those, we usually draw the rest of it.
So we just do like what we were doing at the end of the last chapter, where you just like, you find the one point and you like draw it.
Like the vertex on it, once you find the vertex, yeah, it kind of works like that, yeah, eventually. Okay, so quick review. 3.1, 3.2, we're going to look at something called logarithmic functions here, kind of fun little things, properties of them, and then we're going to look at equations, eventually solving them. So where are we at? We defined it. We did some calculator calculations for it, is that right?
Yes.
Those that were not here, just real quick here, just putting it all together. And then let's go real quick here, defining it back. So f of x is equal to a is called the base, and x is called the variable, is the exponent. Then I gotta see the eyes then, yeah. So let's jam. So a has to be a positive number. It has to be bigger than 0. A can also not be 1 because then we have ourselves a line, and that's not what exponential functions do. So those, based on those two conditions, we're good to go. So we did some calculations by calculator, because you can't do that on just kind of thinking of it. You can't do 2 to the negative pi. It's just not going to work. And then we started graphing them. We noticed that these slopes are from one side, they're just very plain and not as steep, right? And then at some point, it just becomes steeper and steeper. We're good? And then found out if you put a little negative inside the exponent, all you do is just switches it around. Hey, it's a reflection about the what axes? What axis is that a reflection of? This one to this one. X, Y axis, one of them. Y-axis, yeah. It's a reflection about the y-axis. Notice it's the steepness is here, right? Now the steepness is here. So it's a reflection about the y-axis. That's what that does. Okay, and then we just start graphing here. Normally, that's what we do here. It's a one-to-one function, and then we thought about maybe algebra 1, if you guys did these here, solving these equations right here. So the easy stuff to solve is, if you can get them to be the same exact base, then what you do is you just solve for the exponent. That's the solving of equations here, okay? And then we did all this, and then we did something like that right there. So we can move it around. We can move it up, we can move it down, we can move it sideways. We can move all that stuff with exponential functions here. Okay. So now we get into one unusual one. So notice this is a base of 4 right over here. We're going to get a base of, this is a funny little number. It's called base E. Anybody have heard of that before? Base E.
Oh, no, but I was doing science homework and I kept getting E at the end. E minus 4.
Okay.
No.
And it was not.
Give you a number and then it's like a capital E minus 4. You know what that means?
Oh, yeah,
That's for exponents here.
Oh, so it's
scientific notation.
the power of -4?
That's
Whatever small number.
Whatever that number is, let's go for it. Let's do a quick lesson in the calculator here. So let's say you had an answer on the calculator. It said this right here, is that right? So that means it's 3.56 times 10 to the -4. That's that notation.
I always have like 10 decimal places before that too.
Yeah, it's a longer number. So that little -4 just means you go 1, 2, 3, 4. That's the number there. And usually when you go backwards, usually it's when it's a big number here. Your calculator probably can handle that number. It just can't handle going backwards many numbers. So it converts it into scientific notation, and that's kind of like the notation for it. Cool, good. Does that make sense? Okay. quick aside. There you go. Now you see what the calculator does. Okay, so let's do this here. E is a pretty cool number here, but let's go to, I'm gonna get out of here. I think I can do it on this one. Yeah, do this one here. Anybody done Desmos before? How many are familiar with Desmos?
Yes, when I didn't know how to use my graphing calculator.
Cool, okay. So Desmos is a online graphing calculator. It does a pretty good job. I'm surprised. And let me just do this real quick. There's a sign. One second. I just want to try the scientific calculator now. So the scientific calculator, a 4-function calculator. How fun. Let me check out this just for a second here. Never seen it before. Oh yeah, okay, so if you need a calculator that does all that stuff right there, it's online as well. Okay, but we're gonna go to the graphing calculator here. Cool, and here's what we're gonna do. Yeah, let's do this here. Let's do 2 to the x. All right, we know what that looks like. Oh, and you know what? When they put capital letters in here, I just want a regular x here. So caps off. Hey, we know that graph, do we? Four to the x. Oh, we've done that as well. Notice there's like this little small gap, right? The red graph is on top, 2 to the x is on top, 4 to the x is on the bottom. And then at this point it switches. Now the 4x goes faster and the 2x goes slower. That's cool. Okay, so let's do this here. We're gonna do some crazy stuff here. So let's get rid of that. And here's where things formulate. It's kind of funny, I think. How about x to the x? Isn't that goofy?
What happened?
It's x to the x. So it's right. 1 to the 1 will be 1. That makes sense right here, right? 2 to the 2 would be 4. That would make sense, right? But then you also have like 1.2 to the 1.2, right? Or you have 2.8 to the 2.8.
Oh, wait,
What about when it starts going back up on the other side?
That's because 0 to 0 was 1. That's why.
Okay.
And 1 to the 1.
Oh, that's cool. Yes, yes. We should do that here. Yeah. So any number to the 0 power is 1. 0 to the 0, that'd be a fun one. Let me think about that. That's kind of cool.
It can't be a straight line, right?
Well, I
Like
think it's
0, 1,
have
1,
zero.
1. You can't have it straight right there.
But it's not.
So does it have
You get one.
You get 1. Just,
Oh, well, that, and I guess,
just
You know,
So why does it stop there? It looks like negative 1 on the top.
Ah, good, good, good.
Wouldn't it be 1 over the power of 1? Negative 1. Wait, so why does it stop right there? Like when it goes back up on this side, why does it just?
Stops at 0.
Yeah.
Because we can't take like negative 0.5 to the negative 0.5 power. What happens is you're shifting between reciprocal and the number itself so many times that you don't really have a graph. You don't have a consistent graph. Does that make
makes it
sense?
easier.
Sometimes sometimes you can't calculate, like negative 1 to the negative 1, right? You can calculate, it's just a single dot, but then you can't calculate anything afterwards or before it. And so sometimes the calculator will actually put those in. Okay, is that a funky graph or what? What do you guys say? And notice it just keeps on going up, right? Zoom, goes up. So how about this? I'm going to change it up to 1 divided by x. That. That. Oh, I like this one. Let's take a look at this one here. So how about the reciprocal of it? This is going the other way, right?
1 over x. 1 over x.
I don't think I like that.
No. And if you follow it, notice Notice what happens. Notice what happens to the y value right here. The one that changes. The y value goes down to 0.7 now, right? 0.711, and then it's 0.079, and then eventually about right here, boom! It's just a 0 the rest of the way through. Okay. Boom! I can go. That y value is always 0. We good? So it became so small. We know it never touches the x-axis, right? But we know that it's so small that it's just essentially 0. Good. Okay, so let's do one more.
Oh. You.
I agree with all of you.
Yeah. Wait, is there a horizontal asymptote here?
Oh, interesting. I think that's what I want to get to. There's a horizontal asymptote here. And let's see what it goes to. I just want to see what it goes to. So let's see. Dylan, did you have a question? Or did you have...
No, it's just stretching.
Okay.
Does it say x plus 1 over x?
It's 1 plus 1 over x to the x power. And so this weird thing happens. This little guy does not go up to positive infinity. Doesn't go to 0. It just flattens out right over here. So then the question is, what is that number? So we'll go like this. Should we go 2.335? That's great. We go out to 15. It's 2.63. Yeah. 2.652. Let me go out further. I want to see where it gets like more consistent. We
Wait,
good?
like that one heartbeat thing, like guy's dying, so he has like one heartbeat.
And he did. It's still going though. The y value is still increasing.
It is.
Yep. Let's see. Let's go from 2.699, 2.7. Oh boy. Let's go out.
It just looks like a line.
Let's go to 2. Oh, okay. Hold on. So it's 2.7. I got a consistent 2.7 now. 2.71, 2.716. Okay, hold on. Let me go even further here. Let's see. Let me put it on this side. Okay, guys, watch the y-axis here. Tell me where it ends.
I want us to come across a massive spike that's there for no reason that nobody knew about because they never bothered to graph.
And remember, this is increasing in the thousands, right? This is from 3,000 to 4,000, and we have no change, right? 4,000 to 5,000, no change. I think it's pretty consistent. This 2.718 number. Good?
Consistent.
Seems consistent right now. So let's see. Where does it become consistent? About right. Oh, about right there. About 1,600, 1,700, right? We turn 1,700, and it's consistent all the way up to 5,000. So I think that's probably the number is going to stay. Hey, where'd you go?
Gotta check it, 20,000.
There it is. Should have moved.
Yeah, you gotta span like the
Span it?
Yeah.
Okay.
We gotta check it like 20,000. There we go.
Yeah.
Oh, 100,000. Way bigger than I was going.
Oh, yeah, that's the same.
Definitely
It's
2.7.
still the same, okay.
Yep, 2.718.
You never
Okay.
know. Hold on. Technically, you never know if it doesn't change.
Yes, that's why in mathematics we actually have to have proofs.
Also have no.
You can't just say, oh, the graph says so, right?
Like 7 trillion.
Because it says it says so.
Yeah, because it says so. So you have to have proofs for it. So let's jam with this here. So we're going to actually call this a special number. We're going to call it a special number called E. Now, why do we call it E? And it's going to be about, it's kind of like pi. What is pi?
3.1415.
No, it is not. What is pi?
Is it a number?
Hold on.
Oh, no, it's the something with a circle.
It's something of a circle divided by something else of a circle.
Yeah, something with a circle divided. Hold on. So pi equals to, say again?
The circumference. divided by-
Circumference, yes. Diameter, yes. That is what pi is equal to. We good? Pi is approximately 3.14159, blah, blah, blah.
I put that on the test.
Blah, blah, blah. Okay, we good there.
We'll
So,
just keep going.
so pi is equal to something. It's a ratio, right? But whenever we look at any circles whatsoever, large, small, it's always the same. It's always that number right there. That's a fun question to ask. So E is kind of like the same thing here. E is equal to 1 plus 1 over x to the x. That's the equal to part, right? But approximately E is equal to 2.718. In fact, I'll write it in 28 is what we normally use. And then it goes blah, blah, blah. We good?
But why did we just pick that random equation to assign a letter to?
How fun. Oh, what's questions? Why did we pick that one? So where does the letter come from first? Well, it comes from a famous mathematician. His name is this guy. We would have used a G if his name was Greg.
Is that you?
His name is pronounced Euler.
Oh,
He
remember
was-
this? When we had this
Dr.
argument in
Ryan was
stats
very
class about
adamant about
whether
that.
Greg is Euler or Euler?
For what one?
The pronunciation of Euler,
Euler.
very adamant about that. That's the only reason I remember it.
That's why I just never said it because I don't get understand.
So Euler, what he did is he solved a lot of different problems in his day. And then he started really looking at probability, statistics. He eventually started statistics or card counting, or he would just kind of take a game, like you guys are playing this game, let me think of the math behind this game. And so he started a whole, like multiple branches of mathematics. So years later, when we actually discovered this little piece right here, and why do we discover this? Why is this important? Because it occurs in nature and it models nature a lot better than any other exponential function. Or logarithmic function, technically. We change it to that. So in honor of Euler, we discovered this maybe like 50 or 100 years after. But because we want to give honor to Euler, we used E as the name, as a person that has discovered new stuff. Yes, Tristan.
When was this guy alive?
Ooh. 1600s or 1700s? Yeah. Okay, so with that said, are we good? So let's jam. Hopefully you guys have your calculators with you. So now, instead of just E is the number, right? But now what we do is we go even further beyond that. What we want this right here. We want to make this into a function. So we say E or f of x is equal to E to the x. So now we use that as the base. So 2.7 is technically the base. Okay, so it's in between 2 and in between 3. We good? Can you say that both? No, in between 2 and 3. So let's jam. So using a calculator, hopefully you brought it. Can you go to, and let's go 2 decimal places here. So A, you're going to plug in, let's see, f of -2, e to the -2.
That's the F of that.
F of x is equal to e to the x. There's my function. And then we're going to plug in a -2 into it here.
And
So,
how do I make that on?
good. So you guys should have a little function. There's kind of 2 different functions in the calculator. One is the letter E, we good? And one is the variable E. So kind of make sure you guys don't get those mixed up. And I'll bring my calculator up in just a second here.
You want to know something weird?
What is it, the negative
-2, -2. All right, so let's jam. And Charlie, I'm still looking for a calculator for you, good? So let's go for it here. So I think the E is over here. This one,
Is it above the division?
above the division marker, yeah.
No, above the division.
No, sorry.
The second division.
I can't see it very well. No, it's over here with the LN button. See the LN button? You see the E to the X over here?
Yeah.
In between the log and the LN?
Press that button.
So it has to go to the second function though. So it has to go second function and it opens up a exponent. Hey, it opens up the little caret that we have. Remember that little caret for exponent? And then don't forget this is a negative, that's a minus. Don't confuse the two. So -2. And I got myself an answer of 0.135, blah, blah, blah.
Whoa, same.
Are we good? Cool. Okay, can you guys do the other ones here? So can you plug in -1 into it? 0.25, -0.3 into it here.
-1 and 0.367.
Cool, okay.
Don't know what the other.
So this one could be a little important point here. 0.3, 0.37, 0.4 on a graph if we wanted to. Oh, how about this? Let's just do this e to the 0. What's that going to give us?
1.
Awesome. I agree. Check it out just to make sure. Yeah, any number to the 0 power is, hey, hold on. So remember with exponents, we still have the same point that we had before. Remember the 0, 1, 0, comma 1 point? Even this one has a 0, comma 1 point on the graph. Okay, switching it to the other side here. So I got, you guys are already done. I'm just catching up with you guys here. 0.25. 1.28. Everybody agree there? And -0.3. Ta-da, 0.74. Are we good? Cool. Okay. Think we're good there. Let's do a few more things here. And normally, example 7 here is what we want to do is we want to be able to make this a little bit smaller so I can fit it all in here. Can you guys see that though? Right there. Okay. All right, next thing on the list here. Let's go to the next piece to do, which is y equals. See this little y equals right here? Clicking on that. Now we're going to plug in a few points that we studied already here. So how about this? Plug in 2 to the power of this little caret symbol. And this is your variable button right here. So just 2 to the x.
So which one is your greater?
Right next to alpha and underneath mode. Oh, I gotta put
So just do the power of that.
just x, And so remember we graphed this the first time through?
In this calculator, not do curve line. It just like cuts off every time.
Your window's probably off. So let's check Windows here in just a second here. All right, so real quick here, what you can do is actually do this right here, Abe. Go to Zoom and go to Zoom Standard, which is number 6.
Go to Zoom standard. Nothing happens on that.
Oh,
Stay for me. Oh, there we go. And you go down to standard.
6, and press enter. It got back up to like -10 to 10. It became to the standard window.
That function that you grabbed, is that is that e to the x?
That's 2 to the x.
Oh, 2 to the x. Oh.
Yeah. So now we want to go back and let's graph e to the x here. So that little guy is going to change. And the same button over here. We're going to go e to the x. And we should probably clear it out first though. So second, e to the x, and put the x in there. And it should look like 2 to the x, right? Because they're just off just slightly. Press enter. And this time you can just press graph because we've made our graph -10 to 10 here. So press graph. Voila. Are we good?
Zoom in on the numbers a little bit, please.
Say again?
Can you please zoom in on the numbers a little bit?
Oh yeah, absolutely. I got to go like this and like this. As soon as we start graphing them, we haven't graphed them yet here. So now the question is this, can you guys plug in 2 times e to the 0.24x into the equation?
Why you breathe your
Okay, let me plug it in. Boom. So I'm going to go back up to y equals over here. Clear it. So it looks like 2 e to the x, 0.24x. Are we good there? Close off the parenthesis. So you guys talk to me here. And again, if you're having trouble with your calculator, raise your hand. I'll come by. We're good? So are we good? Cool. And let's jam. First graphing, the first one looks like this. Ooh, not as steep when you go out anymore, huh? I think it's because that little 2.4 or 0.24 as a multiplier to the x, it's slowing it down because it's less than 1. Real quick here, before we graph letter B, notice you have a negative in the exponent. What's it going to do? What's the prediction of the graph? This one is, it's going to be reflected along the y-axis, Abe told us, right, last time? Right, whenever you put a negative inside the exponent, it reflects it. So it's going to start off high, right, and it's going to slow down, go down, and it's closer to 0. Let's check, let's see if it does. Let's see, 1/2, you can put in 1/2, you can also put 0.5. 0.5 is the same thing as 1/2, might as well put that in there. E to the negative 0.58x. We good there? Ready for that one? And jam. Sweet, Isabel's right? It goes down now, right? Because it's reflection. We call it a decay curve, which means decay just going down. The other one we call as a growth curve. It's climbing higher and higher. Okay, boom. Are we good there? So let's see, we're able to graph it by hand. We're able to, we'll learn the definition first. Able to compute it by calculator, graph it by hand, learned about E as this important base. And normally we graph E on the calculator. We want to see what that looks like. You can't do it by hand, it just takes a while. Okay, we're good. So let's jam with some applications here of this stuff. First things first is this one here. And probably need to write down these formulas. You'll need it for the homework here. So you have compound formulas. Thank you. Please remind me of zooming in because I forget. So this little guy here. So when we deal with money, any kind of interest, sometimes interest goes against you, sometimes it goes for you. So if your parents own a house, the interest that is accumulated over time you have to pay that interest eventually. The flip side of it is if you put like money in for retirement or something like that, then the money compounds eventually. And I used to teach the business math class way back in the day. And so we've discovered, we're trying to figure out all the different ways we can get $1 million at age 70. So it's like, hey, how about if we do this? How about if we do this? So it was so cool. So if you can put in $15,000 at age 15, right? Just a lump sum and that's it, right? Through about a 7% interest rate throughout the years on average. At age 70, you should be about $1 million. If you don't do that, shucks.
Or just plug in 60. Oh no, I'm just plugging 15,000 plus 7% of that. That's what the calculation is. You can start anyway.
Or
So-
just do it by age 71. It's not that much later.
There you go.
Oh, wait a minute.
The other interesting thing is if you wait till 20, you'd have to put in $15,000 every year for the rest of your life to get $2 million. What? Why is that so?
All right, let's find it.
And so here's a weird thing about compounded interest. And Einstein, when he saw this, he was like, this is such a crazy thing in the world. Okay, here's what happens. Let me go back to here. Hopefully you guys, yep. So just like exponential growth, let's go compounding interest first. So let's say we put in $100 into a bank account. We're good? And let's say we have 10% interest because it's easy to calculate 10%. The next year, just by having the money sit there, right? Just by sitting there, how much money should you have the next year? 110. Yeah, because 10% interest, 110. And then if you go the year after that, what you're going to get? How come you get 121? Yeah, you're getting interest based upon the interest from the previous one. So you get this extra dollar technically in here, right? That you did not work for, did not earn, did not do nothing with. Are we good? And so if you go to here, so here's was $10, right? Here's was $11. Right? What's the interest here? This is going to be what? So notice every single year, we're actually gaining an extra dollar of interest. Good. That does not, like, yeah, an extra dollar, who cares, right? But here's a little problem. But here's what happens here is when you get into, it takes about 50 years. That's the problem, right? When you're about the 50, 55 marker, you're gaining so much interest here that this little guy, the interest is surpassing how much you have in the amount in the account practically. We good? So let's do that. Let's do that actually. Thinking how much, I'll set it up for next time. That'll be kind of fun to sort of see for next time how much that accumulates here. But it's this little extra piece here that keeps on growing and growing. That's what exponential function shows, is that you start off this way. Here's your dollar. Then it becomes $12. Then it becomes $50 of interest only, right? This is just money sitting there. And so eventually you're earning that last year over here between, well, that last year from age 69 to age 70, right? You earned like $80,000 just in interest alone, good, for letting it sit there.
You're saying I should put 15 down.
There you go. Now, does it happen? Does it work all the time? So
Wait, that's assuming you're gonna live on 7.
And assuming you can get a 7% interest rate.
throughout that time, yeah. Yeah, a lot of assumptions when you put in money because you're wagering, you're sacrificing the present for the future, right? What's another thing? If you guys, do you guys remember, or in the year 2000, there was the bubble that crashed, the tech bubble. And so what happened was you have all these companies in the 1990s, they were just growing massively. I mean, we had an explosion of technology. And technology was everywhere, and so there's this big growth. And so the year 2000, there's so much money pumped into companies that they were actually not worth that money, right? So every so often, stock market goes through a reset or just a recalibration of how much things are worth, right? And so what happened there was it went just, I think it went down by 1/3. So you had people that woke up in the morning, had $1 million in their account. And by the afternoon, no, it was more than that. I think it was half. By the afternoon, they had a little less than $500,000 in their account. There's, and I was teaching during that time. And so we had people, in fact, an investor that used to be an investor, he quit his job, became a teacher because he just lost all his money at that point because he was invested for others as well as for himself. And it was a rough patch of time there, early thousands. But anyways, all that stuff. It's just this whole concept of interest can build upon interest. That's eventually what you want. And you're sacrificing the present for the future. So let's do this here. So here's your compounding formulas. This is how we compound or look how much money you have afterwards. A is your balance after 2 years. And so let's not do quarterly. Let's do monthly and continuously. So there's an extra little piece right here for continuous compounding. So this one, let's talk about it here. So on a monthly basis in my savings account, right? They give me interest on a monthly basis. Usually that is, if you have a business, sorry, my savings account, yeah, a business savings account, usually they give you interest every quarter, because that's a sort of business mindset, is every quarter you get something. So there's a quarterly view of money flow. Continuous is what we think about when we think about inflation. And in fact, inflation is tested by having about 100,000 people or so, maybe less than that, maybe like 10,000 people. They go shopping for ordinary products at the store, and they just tack how much they're worth. Right? They'll buy bread, they'll buy cheese, they'll buy not buy, but maybe they'll just indicate how much it's worth. Milk, just some standard supplies, the rice, the potatoes, and what they'll do is they'll figure out how much it was worth then, how much it's worth now previously than the previous month, because it's usually done monthly. And so then we figure out how much inflation we have. Anyways, are we good there? Let's jam. Let's go with B. So here it is. I have a total of $10,000. I invest with an annual interest rate of 9%. Can you give me the balance after 5 years? So I let that sit there. It's at 9%. Give me the total in 5 years.
Yeah, formula to plug in, or we have to do all 5 sections?
Oh, that's right. If we do that, we have to do year 1. Then we have to do year 2, right? Year 3. We don't want to do that. So our formula is right here. We can plug into this little piece right here. Now it'll give it to us right away. So let's go with A equals 1 plus. Now your rate is going to be in terms of decimals, because it's always in decimals. So 9% in decimals. 0.09, perfect. Divided by, and N is the fun one. N is the number of times the money will be compounded or credited to your account in a year's time. So if we do it monthly, it should be 12, absolutely. And then over here, it's going to be 12 times 5, the number of years that we have it in.
Where did he go?
Koichi, sorry, thank you so much. Sorry, guys. That should be the 12,000. Thank you so much, Abe. Else we've been calculating something that does not exist. P is the principal, how much you put in. And then let me get to this little piece here. So go to clear, go to mode, go to the beginning part. So how about 12,000? It's going to be 1 plus 0.9. Oh, thank you. Divided by 12. All right, to the power of, and this one you have to put parentheses in here, or unless you kind of do it yourself in your minds here. 12 times 5 is 60, but if you want to put in, you got to put an extra parenthesis. So 12 times 5. And click enter, and what do you guys get?
18,788.2.
Not bad. I'll go with that.
That, but mine rounded to the second, first decimal.
Okay, Dylan, question.
Where did the
Dylan's question is, where did the 12 for the denominator come from? Came from us compounding it monthly.
What does that mean? Like just 12 represents 12 months?
Oh, sure. It's compounding just means how many times the bank is going to give you the money. And so on this would be like a regular savings account. And at that point, it would be at the end of each month, they'll give you the interest that's added to the account. We good?
So the 12 just represents the months.
So if the bank was giving you money quarterly, then you'd have 4. There are some banks, they actually will say, I'll give you daily. They give you a daily amount. So that would be 365 or 366, depending on the year at that point. Okay, we good there? So quarterly, monthly, daily, every single second would still use the first formula. But if you want to use compounding continuously, which means the bank is going to give you money every millisecond of every single day, and they compound and they give it to you, compound and give it to you. That is something called continuously compounding. And notice that little E is in there now. And so what happens if the bank said, we're going to give you money all the time, as long as you earn like a cent, we'll give it to you right away. And so let's see if that changes a lot. Let's go with the 12,000. And then we're going to write the E function in here. And it's still going to be what? R times T. So the rate is 0.09 times 5 for the time. So what is that? Does that give you a lot more money, or is not that much money? Much more money.
Not that much. I mean, more, but.
And we usually don't, like banks don't usually do that. They don't give you continuously compounding. They still have computers that are running all the time. They'd have a program that runs once a month. They compute the interest, they give you the money, you're done. So this is more like if we were looking at inflation for the most part. Ouch. I want that. I want not that. That's what I hit last time. Sorry guys, we're going through something weird here. 1 second. Put into presentation mode accidentally. There. Okay, let me plug it in here myself, just real quickly here. 12,000 times E to the 0.09 times, is it 5? A little bit over that much money. We good? Yeah, not that much more, because again, the number of compoundings become a lot more, but then the interest becomes less. Okay, so $18,819.75 at that point. Okay, so that was what we call, this was kind of like a business or economics problem here. Let's jump into like science. Where is this used in science? Okay, are we good with those guys? We're good. This just an application of exponential functions here. Oh yeah, 1986. Anybody was alive? Anybody alive in 1986? One.
Obviously.
A nuclear reactor accident happened in Chernobyl. Anybody heard about it? Anybody know about it? Okay, yes, Landon says yes. What do you know about it, Landon?
Well, it was catastrophic.
Yes,
Big meltdown. Lots of radiation. Even now, there's hazardous levels of radiation.
There's like different
You go
levels.
towards Chernobyl, but it's not like. I know a really cool story. There's a lady that lives within the boundaries because it, for some reason, the radiation helps with like her illnesses.
Oh, interesting.
It's some side effect. I don't know. She's kind of crazy though, so there might be a side effect.
There might be another side effect.
There's this show called
Gotcha.
River Monsters where you find like a mutant fish in like a lake right by it because like the radiation like messed it up, so it grew like super size.
We go sci-fi. Dylan?
So if I remember correctly, what happened is during basically a power test to see how much, like, if they're hitting their standards. There's an error with inserting some of the fuel rods,
Very
and they
true.
tried to take it back out, but in doing so, they accelerated the reaction more, and so it just burnt through and melted the fuel rods, and it just turned the entire reactor into a molten lump of radioactive metal that just kept getting more radioactive.
Yep.
Is this the one that we put the dome over? So you put like a
Concrete,
block
yeah,
on top of
block
it?
over. Yeah.
Listen to you for-
My, my wife, she was younger at that time, but when they, so my wife lived close to it. So when it exploded and they found out about it, my father-in-law, they immediately took them and went to a city called Odessa, which is way, way south of it. And they just lived there for the next 3 months. Like, we're not coming there. It was sad too, because the USSR, they used to pay people to go clean up the mess. Like, hey, we'll pay you this much money in a year if you come clean up this mess. Those people never got paid. Nor did they. It's so funny because that would never happen in America because somebody would get sued by then, right, at that point. But well, different country.
They drop a giant concrete block over it. How does that work?
They literally
They
just
built
built
it.
a dome
They built
and
it.
just like clopped.
So I got a quick video. It's only like 3 minutes here. Let's see if this helps here.
The world's worst civilian nuclear disaster took place when a reactor exploded at the Chernobyl power plant in Ukraine, then part of the Soviet Union. Present-day Belarus received 60% of the initial fallout. The radioactive cloud spread further to cover most of Europe. The Chernobyl nuclear power plant was one of the Soviet Union's most advanced facilities. The first 2 reactors became operational in the late 1970s. The 4th reactor was the newest, going online in 1983. On April 26, 1986, technicians prepared to test the backup cooling system in reactor number 4, but the routine safety drill went horribly wrong. A nuclear reactor is like a giant steam engine. Uranium fuel rods react to produce a massive amount of heat. That converts water into steam, which drives huge turbines to generate electricity. Control rods are inserted in between the uranium to slow the reaction. And it's crucial for cooling water to be pumped around the core to prevent overheating. But as the tests began, almost all of the control rods were removed, and technicians lost control of the flow of coolant. Temperatures soared, and extreme heat began to melt the core. At 1:23 a.m., reactor 4 exploded. It spewed 8 tons of radioactive debris into the atmosphere. 115,000 people were evacuated from a 30-kilometer zone around the plant. The battle to put out the fires inside lasted for 15 days. More than 500,000 military and civilian personnel were drafted to deal with the accident and its aftermath. 31 of the initial firefighters and plant workers died within days from acute radiation sickness. The toxicity of the radioactive cloud was equivalent to 400 Hiroshima atomic bomb explosions. Crews hastily built a concrete sarcophagus to encase the entire reactor to prevent more radiation from spreading. Inside, there remained 200 tons of radioactive fuel. The remaining 3 reactors continued to operate due to energy shortages in Ukraine. It wasn't until the year 2000 that the Chernobyl complex was completely shut down. With the concrete sarcophagus crumbling, the international community began to build a new confinement structure for Reactor 4. It stands 110 meters tall, higher than the Statue of Liberty, and it's wide enough to fit a ship the size of the Titanic. At a projected cost of $3 billion, construction is scheduled for completion in 2017. One of Chernobyl's iconic red and white chimneys will be dismantled, and the massive steel dome will slide over reactor number 4. The confinement structure is expected to last for at least 100 years.
Are we good? So let's finish this up here. Let's see. So the explosion spread toxic radioactive chemicals into the air to see what a city is uninhabited. Consider the model. So this is the number of plutonium that still remains from the initial blast. And how far are we going? T is equal to 0. And we're going to T is equal to 100,000. So let's read this here. So to see why the city is now uninhabited, consider this model, which represents the amount of plutonium that remains from the initial amount of 10 pounds after T years. So how much of the 10 pounds will remain in the year 2010? And how much of it will remain 100,000 years later? Whoa, craziness. So let's go with it here. So 10 pounds, 1/2. Let's see, if we start off the year 0 is 1986. You guys talk to me, what's 2010 gonna be? Twenty-four, yeah, 24. So it'd be 24 over 24, 100. All right, we're running out of time here real quick. Let's just do this one then.
Wait, then do 100,000.
The new 100, okay, yeah. We can probably get that in there. Okay, so this is 10 times. I'll put a times in there just to make sure I have it separate here. This is 1/2 times, yeah. 0.5, I'm gonna put in 0.5 for 1/2, is that okay? To the power of 24 divided by 24,100. So not much from the 10 pounds that we have. Are we good there? It's 9.99 pounds still. 100,000 years later. Let's put this in. Let's see, if you push the second button and then press entry, it'll give you the entry back again. You have to do a little bit of work here. So this is 1,000,000 divided by. So this is 100,000 years later. Only about 0.5 pounds will be left. And I watched their documentary recently, and they said that there are, even now, there are small animals that are making their way back into the area. I thought that was interesting. Anyways, with that, we are done. Come with homework questions from 3.1 on Friday. I know we do. Have I sent a homework to you guys or no? Oh, okay. I will send it. Thank you so much.
They said
See
two people
you,
pictures and they never came back out.
See you guys. See you, Dylan.
I sure know what they're really